All right, so let's start today. I'm gonna start a brand new topic. So if anybody has any questions or anything that we covered over the last 2 weeks, you can ask now because we're gonna start a brand new topic. Does anybody have any questions? Okay.
Regarding the homework,
Uh-huh.
question 15. So it was
I don't remember the question.
Yeah, it was a frame that had 2 pins at the bottom
Mhm.
and then a hinge connection at the top left
Okay.
with a distributed load on top and a
Well-
horizontal load to the left.
Well, I can't put the whole problem. How about like anything related to the homework? Maybe I can meet you guys after the class and we can discuss it
Okay.
together if you guys have time. Also, if you have, this is what we can do. If you have a question, I try to answer in the emails, but if you have, that's actually what I followed over the last few years. If you have a question, nobody send me any message on Canvas at all.
No, I don't think so.
So, if you have a question, take a picture and ask the question clearly and put like whatever you want to know on the figure and send it to me, and I can answer to you on Canvas. Things when you send me over emails, and sometimes I get messed up. I try to search on my email, but sometimes I can't find it. But I try to answer you as soon as possible. That's related to the homework.
Are you gonna post the homework solution after
Yeah,
this too?
after the deadline, is the deadline passed?
Today.
No,
Today, so after the deadline, I usually, yeah, so how about that? I'm
Yeah, so
gonna
we
post
can
the
check.
model answer, and then you review, and if you have a question, you can come back to me,
Sounds good.
alright? So, okay, so all the questions was related to the homework.
Yes.
Cool. Alright, so today we are gonna start a new topic. It's the analysis of cables and arches. So have you guys had any background on analysis of cables and arches before? Alright, so let's ask a really like general questions. What makes us as engineers would go to the arch and cables solution? Like why would we use arch and cables in a structures? Big spans. And why big spans? Like what is the special about big spans? What big spans do to the regular structures?
More aesthetically pleasing.
More what?
Aesthetically pleasing. The architect
Like
wants
it's
that.
not about static, but it kind of, but when we take this to the internal forces. Okay? So let's talk about the systems that we have as engineers, all right?
Or less unknowns.
Okay. What was that?
Less unknowns.
List nodes?
Unknowns.
List and nodes? Well, actually, you mean in arches and cables?
Well, yeah, because if you have more columns, there's
Well,
more supports, more unknowns.
Absolutely, that can be arches is more determinant than the regular structure, but that's actually will take us to what we're going to talk about today, like the most simple systems and all the structures that we see. It's called the simple beam system. This one. All right. So this is the most simple system in any structure. Why is that? Because the thing is, it's very easy to get the reactions. It's very easy to solve. And the thing is, when it gets heated, there is no internal forces going to develop. That is the most easiest system. The second one complex after this one is the continuous beam system, something like that. All right. The thing is, let's say that we have a span. This span is like 30 foot of length, like 10 meter. Okay. Let's say this span is 10 meter. And let's say this span also is 10 meter. All right. So you have a 10 meter here and 10 meter here. Can you tell me which system of these is more economical? The
Depends.
second one or the first one?
Depends.
Which one?
Depends, I guess.
It
Because
depends on what.
well, you're gonna have to have stronger concrete, more steel in the one with less supports.
Well, the thing is, let's think about it. What makes a cross section? Let's think about general. The thing that makes a concrete expensive is the steel. The most expensive component when we do reinforced concrete is the steel. Even when you do steel structure, the more that you have steel, the more it's gonna make it more expensive. So let's think about it in a steel wise. Which one of these is gonna have more steel? This one or this one?
Right one.
Why?
Because you have, even though you have 10 meters, you have to, you'll need more steel area and reinforcement per se.
I just need one word. There's one
Tension in the
thing.
bottom.
Hmm?
Loss lots of tension in the bottom.
It's coming from what? From more bending moment. Here, what is the bending moment here? It's gonna be WL squared over 8, right? The thing is, here, like let's say this is 10 meters, so this is gonna be 3, for example. Let's say this is 4, and this is 3. So the bending moment is gonna be something like this. So what happened here? Like, let's say that the span is 10 meters and we have 2 as a distributed load, so we're gonna have let's say that we have W is equal to 2. So we're gonna have 2 multiplied by 10 squared over 8. This is gonna be 200 over 8. Can you guys calculate this? So
25.
25? Okay. So 25 ton meter. Okay, if you came here, what happened to this bending moment? We distribute it, like we make it like a little bit positive, a little bit negative, a little bit positive. So you will find that the bending moment here is like WL squared over 24 or something. Very small value. So when the bending moment is less, that means less tension, that means less reinforcement. And let me tell you something. And this advice or this statement, keep it in your head as a structural engineer your whole life. Our biggest enemy when we design reinforcing concrete sections is this, the bending moment. The more that you make it less, the better engineer you are. The better the system is, the better that makes the bending moment less. So our biggest enemy as a structural engineer is the bending moment. And when I shifted from a simple beam to a continuous beam, I made the bending moment less. And once the bending moment less, you are spending less money. So your clients are gonna like you. And your boss is gonna like you because you are selecting the most economical system. Can you guys tell me why, as a structural engineer, the bending moment, why as a structural engineer that the bending moment is our biggest enemy? Let me repeat it. The biggest enemy is the bending moment. The less the bending moment, the better is the less cost. So can you guys tell me why bending moment is our enemy?
Because you need more steel to hold
Well, very close. Bending moment is our enemy because it's a sneaky internal force. It is not a direct internal force. If our internal force in the structural member is a tension, you know you are going to put a steel. If our internal forces in a cross section is compression, you know you are going to put concrete, because concrete is very good in resisting the compression. Steel is very good in resisting the tension. The thing is, bending moment is a combination between tension and compression. Make both at the same time. Like, look at this. Like, let's say here. Do you know what's going on here? What's going on here is that you have a cross section like this and has a bending moment. The bending moment do this. Put the lower area here under tension and the upper area under compression. So let's put it that way. So let's say this area is all under compression and here's under tension. So what we do is, where we have tension, we put a steel. Where we have compression, we put more concrete. But the thing is, we cannot like make our cross section like a part of it concrete and a part of it steel. So what we have, we are losing more concrete in the middle that we don't need. Here. This is all cracked. Sometimes we don't consider it the cross section. Actually, when we design reinforced concrete, we make something that's called idealized section. We consider all this big part as the effective concrete that goes in the design, and only this steel that goes in the design. How about the concrete here? We don't consider it because it's mostly cracked. So, as I said, bending moment is our biggest enemy. It's a sneaky internal force. It is not tension, it's not compression. It's both at the same time. Okay? So that's why we always have to take care of it. So the less the bending moment, the better is your structure. Or it's not the better, it's less cost. But the thing is, it comes with a cost. Like let's say, oh, I shifted from a simple beam to a continuous beam. So once I did this shaft, I added 2 more columns. So the architecture might be pissed off. Like it's like, oh, I don't want these 2 columns in my span. So it's like, But this is gonna cost you double this. I don't care. I'm gonna spend money, but I want my space area to look good. Okay, sometimes it goes out that way. So this is kind of one of the systems. Okay, you will tell your client, oh, I have a better solution for you. What if I made this as a frame? Something like this. And I made this, and that, and I covered your 10 meter also without columns. So there's no columns. You will tell me, but it's gonna be the same like this. No, it's not gonna be the same. Here the bending moment is gonna be something like this. Like once you draw it, it's gonna be bending moment like this. Here the bending moment is less than this value. Why? Because the bending moment at the top here, all this is WL squared over 8. So this is definitely maybe half, or at least 3/4. So frames is more economical, but it takes a lot of cost when you construct it. It's a special, you have to design this to resist the bending moment that is gonna develop here. If you didn't design this connection to resist the bending moment, it's gonna act as a simple beam. Actually, in real life, it come across like this. Both of them look the same. This system and this system, they look the same in real life. You will find that you have a column like this. And both systems, you will not see anything. From the outside, both systems are gonna look the same. So what is the difference? What is the difference between them? The way that you put the reinforcement inside. If you put a reinforcement at this joint to resist this bending moment, so it is gonna absorb some bending moment from your cross section. But if you didn't, it's gonna act like a simple beam. How does that happen? If it's a simple beam, you put your reinforcement is gonna be look like this, and the reinforcement in the column is gonna be something like this. But if this is a frame, this is actually how we make it. You have to put a reinforcement to resist the negative moment, something like this. It has to go a little bit here, the development length, and a little bit development length. Same thing, like here, the bending moment is gonna be something like this, and then here. So you have to reinforce this cross section in a way that this joint can absorb some moment. But the thing is, once you start putting the load here, this beam is gonna bend, and it's gonna see if this is gonna absorb moment or not. If this is not stiff enough, it's not gonna absorb any moment, and this is gonna develop the whole WL squared over 8. But if this is very stiff and make it like a fixed, is making this joint is kind of like fixed, but it's not fixed. Look at this. Why moment developed here? Because this is semi-rigid connection. This is a flick. This is actually a hinge, 0. It doesn't take any moment. So the more that you make this joint more fixed, the more it's gonna absorb more moment. It is not rigid, it's a semi-fixed, okay? So the way that you put reinforcement here is gonna affect how your system is developing. So as I said, it's all depends on how you put the reinforcement, how you make your design. But at the end of the day, moment is our enemy, and we have to make it less. And we have to pick the system that makes the bending moment less. There's a lot of system that has been developed over these, like, I don't know, over the last few decades that can play with the bending moment, make the bending moment less. Have you guys heard about the post-tension concrete and the pre-stressed concrete? All of this is also because of the moment. Do you guys know the concept? The concept is for pre-tension and post-tension, it's basically, let's say that this is my slab system or my beam system. I know when I put the loads on this beam, it's gonna make like this, so it's gonna have a lot of bending moment. So the post-tension is, it says like, if I put a wires inside my beam, like this is my beam, and I'm gonna put the wire here, and I'm gonna apply tension on this wire, pull it, and then pour the concrete. This is called pre-stressed. When you put stress on the concrete before or after, this is post-tension or pre-tension. But either concept is the same. So the thing is, once you leave the tension after the concrete is stiff, this beam is gonna make like this. This beam is gonna go up like this, because the thing is, you put the tension a little bit under the center of the neutral line of the beam. So the beam is gonna make like this. So the beam is already have a counter moment before the moment that is gonna develop from the load. So once you put the beam on the columns, the beam is going like this. So once you put the load, so the beam is gonna be something like this. So you already countered the moment with pre-moment before the beam gets the load. So at the end of the day, the moment is getting canceled. This decreases the amount of tension down and make the amount of steel less. Sometimes pre-stressed concrete go up to 100 feet, 150 feet. Okay? So that is the concept. So the concept of post-tension and pre-tension is also to resist the bending moment. Also, there's some ideas. Have you guys heard about the hollow core slab? The hollow core slab is something like this. They said, all right, I know that I don't need the concrete because I know this part is compression and this part is tension. So I need the steel down and I need concrete up. All right? So I need this part to be hollow. So how to do it? They make something like this. They make circles, and this circles, here is the steel in this areas, and the concrete is up there, so that they can decrease the amount of concrete. So that's also one of other systems. There's something that they put some balls inside the concrete to make it like to decrease the amount of concrete in the area that you don't need. Same thing with the ribbed slab. They make like ribs, and so that they can only use the concrete in the area that we need. Arch is one of the most innovative systems, and also cables. So cables, that's actually the topic of today, but this is take us to the same concept. So arches and cables, they only have either tension or compression, but let's actually work it out. So if you have a cable, do you think that the cable can take compression? Cable only take tension. So basically, they convert all the internal forces into tension. All right, so that's what cables do. So cables is like, it's basically, you have like something like this, like, let me get a cable. So let's imagine this cable. This cable actually is something like this, but the thing is, once you put load and keep, if you guys have seen the cable bridges, state cable bridges, or suspended bridges, the cable is something like this, and there's loads come from it all the way down. So the cable is supposed to be straight, but once you put the load, it's gonna take a curve, all right? But it's still, all the loads are tensions. Cables are very, very effective systems when it comes to large spans, but the only bad thing about it is the construction and also the deflection. There's always sagging. So and also the anchorage. The thing is, can you imagine a stay cable bridge or suspended bridge like the one Golden Gate Bridge? Can you imagine the cable diameter? The cable diameter that hold the whole bridge is like 1 meter, like 3 feet. And this one, can you imagine the amount of anchoring that you need for this cable? It's a lot. That's a huge design. So the anchorage system for the cable is one of the challenges, and also the amount of deflection that develop in the cable. That's for cables. Arch is kind of like, okay, let's put this that way. Like if I have this system, do you remember this system?
Yeah.
What is this system?
Unstable.
Geometrically stable. Why? Because 3 hinges on the same line. But once this hinge go up a little bit, is that geometrically unstable? It is not. Why? Because it's like an arch right now. Once you put load B, this load B is converted to something like this and this. This is the same if you have an arch like this. And there is something like this, and you have a load like this. So basically, arch, like once you make this like an arch, it converts the bending moment into a compression force. That is actually what is good thing about the arches. It converts the bending moment to compression force. You will tell me, okay, is it gonna have pure compression or there is still some bending moment? It depends on the curvature of the arch. It depends on the shape of the arch. There is a specific design for the arches. It's called funicular shapes. If you got to that shape, you can have the arch have pure compression. Because the thing is, it's like sometimes like you make it all the way up. Like let's say, well, okay, let's think about this one. Like this one, you tell me it's geometrically unstable, right? But the thing is, let's say you put the load and then this thing came to be like this and it's gonna be deformed and it's gonna come to here. Once this system come to the stable shape of it, it becomes stable here if it comes to that way. Like since this joint move away from these three, it becomes stable. Or this joint is up a little bit, it becomes stable. The problem is the three hinges on the same line, they are gonna drop down. Or actually if you put a force up, it's gonna go up. But once it reach up, like once you put them that way and there's hinges at the end, so no, there's no way that it's gonna go down. It's gonna make like a truss system. This one. And actually truss system also one of the innovative system that doesn't have bending moment because it transfer all the bending moment into tension and compression. If you guys remember, like if I have a truss system like this, if you had a bunch of loads, by the way, this truss system is under bending, but the thing is, the bending is getting transformed into tension in these members and compression in these members. Oh, it should be that way. We transfer the bending moment into tension in the lower members and compression in the upper members. That's what happened in the truss system. So truss system, arch system, cable system, it's kind of like ways that we use so that we overcome having a bending moment inside our cross sections. Did you guys understand that? So by the way, understanding the structural system is more than important than solving the system, because you have to understand what is this system is doing to your structures, okay? And all what we are talking about is gravity system. We didn't get even to the lateral load system. Like when there's an earthquake, there's multiple systems to resist the lateral load. There's systems called shear walls. There's system called frame the tube structure. There's outriggers. There's a lot of stuff. But this is all to resist the vertical loads so that we can make the bending moment less. All right, so we have a little bit of background about these systems. Let's actually see how the system look like and what is its characteristics. Okay, let's just start with cables. Okay, cables is something like this. That's a cable. And let's say there's a hinge here and there is a hinge here. So let's get to some definitions. The line between the two hinges, the straight line, this line is called chord. The distance in the middle to the top is called sagging, or any distance like from the chord to the perpendicular distance. This is called the sag. All right. Okay, so this is about the arch. So I was saying here that the cables are used for long span structures like suspension bridges, as I said, and also can be used in roof covers for stadiums. Sometimes when you have a stadium with a very long cover, with a very long span, sometimes you make a cable to hold like a shell system for this stadium. And the challenge is to prevent large displacements, which is the sag, and also to provide efficient mean of supporting at the anchor here, like at the support here, which we call it anchoring, okay? All right, and I say here, if a cable only support vertical loads, like if this cable has only vertical loads, the horizontal force in the cable is always constant. And what does that mean? Okay, this cable has support A and support B. So definitely I have a reaction R, let's say Y, YA, and let's say I'm gonna say that this is the horizontal HA, and this is YB, and this is the horizontal HB. And this cable has some loads, something like this, and they are all vertical. So when you cut in this cable, let's say I'm gonna cut here, and I wanna look at this cable. So this cable is gonna look like something like this. What happened when you cut in a cable or you cut in any cross section? All the internal forces are gonna show up. If we cut in a frame, normal, shear, and moment are gonna show up. How about a cable? When we cut, what is gonna show up?
Only tension.
Only tension, because cables doesn't have compression, it's only tension, and doesn't have shear, and doesn't have moment. Like if your cable is like this and you try to bend it, it's not gonna resist you. If you try to shear it, it's not gonna resist you, but if you try to put tension on it, it's gonna resist you. Cables only has tension. All right, so what is gonna show up here is the tension inside the cable, something like this, T, all right? So the T has two components. It's gonna have a horizontal component and also a vertical component. And we know that there is a Y reaction here, YB, and horizontal reaction HB. So if there is no horizontal forces on the cable, and that's usually the cases in most of our structure, when we have a cable, most of the loads are going down. Like, do you know the transmission towers? They transmit the electricity by cables. This cable has load. Do you know what is the loads that the cable has?
Gravity.
And what does that mean? Their own weight.
Yeah.
The own weight of the cable is the load. That's why there is a sag. When you have this cable is like at 1 mile without any support, it's sag under its own weight. And its own weight is a distributed load. That's a load. Sometimes the cables, like the suspension bridges, you have one big cable and there is loads coming from the small cables that hold the bridge. So most of the loads are vertical and are gravity. So I don't have any horizontal loads. Like, let's say all the loads are something like this. So if you apply the equation, summation of the forces in the x direction and the cable is equal to 0, and this is the positive direction. So you are gonna have that HB minus H is equal to 0. So H is equal to HB. The horizontal force is equal to the horizontal reaction here. If you cut here, the horizontal force is going to be equal to the horizontal here. If you cut here, 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 the horizontal force in the cable is going to be equal to the reaction outside, and all of them are going to be equal to H. One horizontal force. Yeah.
Why don't you include T with the angle?
T?
Yeah, the tension with the angle. On the
I don't understand the question.
so usually when we have something like that and we're looking for all forces of the ends, we have to also add T and the angle.
Yeah, I'm gonna put the angle, but I'm just looking at H right now. So right now, in a little bit, I'm gonna talk about this angle. All right. So we are done with the H, right?
Just I think H is the T cosine angle.
Yeah, we're gonna do it right now. So-
H is T cosine
But my
angle.
question is, why is not included when you're looking for X?
Because that's H.
That's
H
not, okay,
is
right now I'm getting only the forces in the x direction.
Yes.
So T is not in the x direction. The component of it, H, is in the x direction, and H is equal to T cosine theta.
Yeah.
Oh, okay.
Alright.
That was my question.
So
Thank you.
if I put T here, yeah, that's gonna be like not right. But H is the horizontal component, and V is the vertical component. And I'm gonna talk in a little bit about this. So, but I just want to make sure that we understand the concept that the horizontal force in the cable is constant across the cable. What is it that's changing? Is the vertical force. Why? Because the more that you cut here, you are losing some vertical load. So V is it changing, and that's actually what is it changing T. Okay? So, and also what is it changing T is the theta as well. So I'm done right now with H. So I know that H right now is equal to T cosine theta. Like the thing is, if I cut here, oh, I have it here. So I'm gonna put this as theta. So T has two components. This component, one of them horizontal, one of them is vertical. The horizontal one is the cosine component, and the vertical one is the sine component. Is equal to T sine theta. So right now I have our verse rule that the horizontal force is equal to the tension in the cable cosine theta. So there's a general rule in the cable. The tension in the cable at any cross section is equal to the horizontal force over cosine theta. That is our verse rule. So horizontal force is always constant. Here is equal to this reaction. So the only one that is changing is the theta. Like the theta is the slope of the cable. The slope here is something like this. The slope here is something like that. Something like this. So this is the theta. This theta here is almost zero. Here's the theta. Here's the theta. Here's the theta. Okay? So sometimes you will have to do some geometry while solving the problems. Like you will have to use, I don't know, like I'm gonna give you some dimensions and you have to find what is the angle theta. Or I'm gonna give you a curve and then somehow you have to find the angle theta from the curve. Like let's say I give you a curve and I told you this curve, the function is y equal to 8x squared plus 2x plus b. Try to find the angle theta here. What are you gonna do?
derivative.
How?
What?
I'm gonna differentiate this curve at this point. So I'm gonna get dy dx. I'm gonna solve this. It's gonna be 2ax plus 2. And this is equal to tan theta. The derivative of, do you guys remember this stuff? Okay, so the derivative of the function of the curve at any point is equal to d theta, because we know that tan theta, like if you have a theta, and this is x and this is y, so tan theta is equal to y over x, right?
Mm-hmm.
Same thing, tan theta is equal to the rate of a change of dy dx. So we have it that way. So sometimes I give it that way, or sometimes I give you something that is really direct, linear, and you find x and you find y and you get theta. Are we all on the same page?
Yeah.
Okay. So this is our main rule for now. We are gonna have another one in a little bit. Not sure, should be now, no. Let's solve a problem and then I'm gonna introduce our second rule. So the takeaway from this is that the tension in the cable equal to the horizontal force over cosine theta. That's what we need to know for now. All right, let's solve an example and see how cables look like. So I have two loads. This is my cable. It's 3 pieces, 3 segments. A, B, C, and D. 30 feet, 40 feet, 30 feet. And I have 12 kits, 12 kilobound, and 6 kilobound. And I ask you to first to find the internal forces in these cables. Find the tension here, find the tension here, and find the tension in this cable. Let's see, and I give you one dimension. I give you that this dimension is 6 foot. And I didn't give you this, and I called this is H1. And I ask you also to find the value of H2. Let's see how we can solve this cable. So the first question is to find the sag at point C, which is H2, and find the tension in each cable. Let's see how we can solve. Solving any structure analysis problem, you have to find the reactions first. Any structure analysis problem, either this is structure analysis, a cable, a beam, a frame, we have to find the reaction. All right, let's see how we can do it. All right, so what reactions do we have here? At this support I have
RA and RX.
I have
RA,
RA, RX, let's put it R, let's
Y.
Y,
AY.
let's put it AY. And let's see what I name it here, AY, yeah. And this one is DY.
AX.
How about here? There's a horizontal, right?
Yeah.
So I can right away call it as H, and I'm gonna call this as an H.
Okay.
I'm not gonna call it HA and HB because I know there's no horizontal forces, so HA is equal to HD, and they both equal to the same horizontal force. Are we good at that?
Yeah.
Okay. All right, so let's find these reactions. Like, we're gonna solve this like solving any structure analysis problem. To find dy, you have to take the moment at A. You find A, you have to take the moment at H. So I can do that easily. So I'm gonna say that the summation of the moment at A is equal to 0, and I'm gonna assume that the positive bending moment is going that way. So doing this is gonna have, I'm gonna have like negative, this moment is gonna be negative because I assume that this is the positive. So negative dy multiplied by 30, 40, so multiplied by 100 foot, plus 12 multiplied by 30, plus 6 multiplied by 70, all this is equal to 0. Solving this equation is gonna give you that dy is equal to 7.8 kips, kilopound. All right? If you want to find the reaction at AY, you take the moment at D. So I'm gonna say summation of the moment at D is equal to 0. I'm gonna also assume that the positive is that way. So I'm gonna have positive AY multiplied by 100, thinking more about this one, minus 12 multiplied by 70, minus 6 multiplied by 30, all this is going to be equal to 0. So AY is going to be equal to 10.2 kips. Does anybody have any problem with that?
On the test, you want us to do it like that, or can we just like also do summation of y? And
You can do summation of y. Like actually, maybe it's much easier. Like once you get this one, you do the summation of y, you get AY 10.2. Both are good. All right, how can I get H? Does anybody have any idea? All right. Yeah.
oh yeah, we just like grab the section from A and then we cut it.
This section from A.
Yeah, like the cable.
This cable. You mean
Yeah.
like I cut at this section,
Yes.
and what is gonna happen? Once I cut, what should I do?
Tension, you find the tension in the cable. Or you want to use H.
That's right. But the thing is, there's much easier way. Do you guys remember the moment at the intermediate hinge? Like if I have a structure like this, and I have a hinge here, and I have a hinge here. So what we do, we used to take the moment left, like I can get these reactions using summation of the moment here, summation of the moment here, I get these two reactions. If I want to find the horizontal, what I do, I usually take the moment left, and only this force is going to show up, and I can find this easily, right? And I can do the same, the moment right, and I can find this reaction easily, right? That's what I do when I have intermediate hinge. I take the moment left or the moment right, it's going to give me a very simple solution. Cables are very interesting in this. You can consider every point on the cable as an intermediate hinge, because every point on the cable has moment equal to 0. So the thing is, if you come here and take the moment, you can take the moment left and say that the moment is equal to 0. Because the cable only has tension, doesn't have compression, doesn't have shear, only has moment. So you can take the moment here or here or here at any point and say that the moment is equal to 0. You can deal with it as an intermediate hinge. I'm going to show you how we're going to use it. Yes?
Oh, no, I was gonna say that we can do the sum of moments in the 12 caves point.
This point,
Yeah.
that's what I'm going to do. But why? But the thing is, if you do it, like let's say, you want to take the summation of the moment for the whole structure, right? The problem was that once you take, that's really valid. The summation of the moment at this point for the entire structure is equal to 0. And here, the summation of moment is also equal to 0. But the problem was that once you take this, you are going to find out that h multiplied by 6 positive, and you have another h multiplied by 6 negative, they are going to cancel each other. So you are going to end up with an equation that doesn't have h. Try to make it at home. Take the moment for the whole structure. You are going to end up with an h multiplied by 6 positive and h multiplied by 6 negative, and they are going to cancel each other, and h is not going to be in the equation and is not going to help you. Try to do it at home. But what I'm going to do, I'm going to also take the moment at B, but I'm going to do it in a different way. I'm going to say that the moment at B, just for this part, is equal to 0. And if you can do it from the other way, is it still equal to 0? That is what is good about the intermediate hinge. Same thing. At this intermediate hinge, you can take left, you can take right, you can take for the whole structure is equal to 0. Okay? Do you guys got that? What we did here when we say that the bending moment for the whole structure is equal to 0 is valid for any stable structure, even the simple beam. You can come at this simple beam and say that the moment at this point for the whole structure is equal to 0. But you have to take left and right. Because if the moment is not equal to 0 at this point, that means that this section is unstable. It's going to turn that way. All right? That's actually what makes it stability, is that the summation of x and the summation of y and the summation of moment at any cross section, at any point in the structure, are equal to 0. That means that this structure is static and doesn't move. Okay? But intermediate hinges are making something special. It says that left and right are equal to 0. Same thing with cables. All the left is equal to 0. So how we can solve this? Alright, so I'm gonna say that the summation of the moment at B, and I'm gonna say that the moment positive is that way, and I'm gonna say this is left. I'm taking from the left, is equal to 0. So let's say what we have on the left. We have h positive multiplied by 6 minus ay, I got ay is equal to 10.2, multiplied by 30 is equal to 0. Then I can find the value of h. The value of h is going to be 51 kits. Did you guys get that? Like the hinge and moment left and moment right. Once we have an intermediate hinge, that means left and right are separately equal to 0. Okay? And why is that? Like this hinge, the structure that I drew here, like the one that I made like this, was hinge, and here was hinge. In real life, it is something like this. Actually, they're providing support to each other. This can be something. You can represent it with something like this. Here, they are kind kind of rested on each other here. It's kind of like you are having a hinge here and your structure here, and another one is a hinge here and a structure here. Okay, so the moment here is equal to 0 for this structure, and the moment here is equal to 0 for this structure. That's what intermediate hinges doing to the structure. So what is special about intermediate hinges? That the moment is 0 left and 0 right. Okay, so we solved for the horizontal force. So the second question, what is the value of H2? Well, I'm gonna use the same concept. If I wanna find H2, I can get the moment at C. I say the summation of the moment at C is equal to 0, and I'm gonna make that the positive is going that way, and I'm gonna say I'm taking the moment right. The moment from the right side only. So the moment from the right side is gonna give me that dy is gonna be 7.8 multiplied by 30 minus the horizontal force, which is 51, multiplied by H2, which I don't know, is gonna be equal to 0. So I have an equation similar to this equation, except that the unknown here is the sag. In this equation, I know the sag here, but I don't know the horizontal force. So here you can find out that the sag is equal to 4.6 feet. Does anybody have any question? All right, so let's get the tension in each cable. Let's take the cables one by one. And I'll put it here. Alright, this is our first cable. I'm gonna take them one by one. It's something like this. The second cable is something like this. This is A, B, this is B, C, and cable number D is something like that. This is C, D. So once you cut in AB, the tension is going to show up something like this. This is the tension. This is the horizontal force, and this is the vertical force. And actually, this is the theta. If you want to find the value of the theta, we know that this is 30 foot and this is 6 foot. So I know this angle is theta. So basically I can get 10 theta. 10 theta is equal to what? Can you guys tell me what is the
6 over
6
30.
over what? The opposite over? So 6 over 30, right? This over this. And how can I find theta? You get the theta is equal to the tan inverse of 6 over 30, and you will find that the angle is equal to 11.31 degree. So I got theta here. The second step, it's very easy. We just made a rule here that T is equal to H over cosine theta at B, right? Because that's here. So I got the horizontal force was equal to 51 over cosine 11.31. This is gonna give you 51.98 kips. That is the tension in cable AB. So if you wanna find the tension in this cable, the tension in this cable is gonna be something like this. You can get it from this way if you want, but I'm gonna get it from here. This is the tension. The angle with the horizontal, this is the angle. And if I want to find this angle, it's equal to this angle. And I want to find this height and this length. This length is 40 feet. That's very easy. Can you guys find the vertical?
1.4.
It's going to be 1.4. Why?
6 minus.
Because I got 4.6, which is this height. And this is 6. So the difference here is 6 minus 4.6 is equal to 1.4. So tan, this is tan theta at, let's say, B left. And let's see, this is tan theta B right. And this is gonna be equal to 6 minus 4.6 over 40. So it's gonna be 1.4 over 40. So theta is gonna be equal to 2 degrees.
Bless you.
Thank you.
Number 2, so the tension in BC, using the same rule that we are using that you should memorize, is gonna be H over cosine B right, and this was H over cosine B left. So H is gonna be equal to 51 over cosine 2 degrees, and this is gonna give you 51.03 kips. How about this one? This one, the tension at C is gonna be something like this, and this is the angle with the horizontal, so theta, and theta is gonna be equal to, this is 4.6, and this is 30. So I'm gonna say that tan theta C is equal to 4.6 over 30. So theta is gonna be equal to, once you calculate it, it's gonna be 8.7. And so the tension in this member, TCD, is gonna be equal H over cosine theta at C, and this is gonna be 51 over tan cosine 8.7, and this is gonna give you 51.62. Yes. Does anybody have any question? Is it difficult to calculate it that way?
Cannot the TAB be calculated also with the square root of H and AY?
Yeah, you can do that. Like if you were able to get V and if you're able to get H, you can do them, which I believe is gonna be something to the values that here. You can do that. Yeah, absolutely. All right, so I want you to notice something. Can you see the values? 51.98, the biggest. The smallest, 51.03, 51.62. Where's the first notice is that the biggest the theta, the high the tension. So the more the theta, the higher the tension. Why is that? Because the T is function H and cosine theta. So if theta is getting high to be like 90 degree, like here, like let's say 90 degree, that means like, okay, let's say this is the anchor, and the cable can be that, or can be this, or can be this, this, until it goes all the way up. So theta can range it from 0 up to 90 degree, right? So if theta is 0, cosine 0 is equal to 1. So tension is going to be equal to the horizontal force. Okay? So the thing is, it's going to be equal because it's horizontal. There's no way that it's going to develop vertical. But if the cable is vertical and you have load going that way, so the tension is going to be equal to the vertical force. I mean, not the vertical, like, okay, let's say but theta is going to be equal to 90 degree.
0.
So,
Say 89. 89 degree.
okay. So if theta is equal to 90, this is going to be 0, so that means that T is equal to H over 0, which would be infinity, right? That means it's very, very high. So it ranges from here up to here. But if you have it like this, it's going to have like pure tension, okay? All right, so let's put that away. The main important rule that we take it from here is T is equal to H over cosine theta. I want to do something here. I want to introduce something. It's called the general cable theory. What is the general cable theory? The general cable theory is this one and this one. Look what we did here. We multiplied. We want to use that the moment at the cable at any point is equal to 0, left and right, is leading to a general rule. This rule is H multiplied by the sag at any section Z in the cable minus the moment at the beam at this section is going to be equal to 0. Or the moment at the at this section. So what this exactly mean? This exactly means if you draw the equivalent beam of the cable and you get the moment at the cross section corresponding to the section that you want to get the you want to get the sag at is going to be equal to 0. Okay, this is our cable, and I'm going to draw a simple beam like this, and having the same length, and I'm going to put the same load. I'm going to have 12, I'm going to have 6 at the same distance. And you draw the bending moment that comes out from these loads. If you draw the bending moment, or you get the reactions is going to be the same like this reactions. You are going to have 7.8, and you are going to have 10.2. And if you draw the bending moment, it's going to be 10.2 multiplied by 30. So you are going to have a moment like this, and a moment like this, and this. And the value of the moments as these points is going to be equal to, actually I didn't calculate them here, but it's going to be 10.2 multiplied by 30, and it's negative, it's, this moment's supposed to be positive, not negative. It's negative in the, here. And this one is going to be equal to 7.8 multiplied by 30. That is the bending moment for this beam. So the general cable theory, it says, if you draw the equivalent beam of the cable, and you put the load on this beam, this rule, the horizontal force multiplied by the height of the cable, the sag at this point, is equal to the bending moment. How? This is h, so I'm gonna put h multiplied by h1 is gonna be equal to this moment, which is 10.2 multiplied by 30, and actually that's what we did here. H multiplied by 6 minus 10.2 multiplied by 30. You can apply this here. The horizontal force multiplied by H2 is equal to 7.8 multiplied by 30. 7.8 multiplied by 30 minus 51 multiplied by H2 is equal to 0. So that is the general cable theory. I have one page here. I tried to prove it using symbols, not numbers. Like I put load equal to B1, B2, or distributed load, and try to work it out step by step. You can follow on it at home. Like try to do it by yourself. And this is the proof of the general cable theory. I'm not gonna ask you in the exam how to prove it, but you should know how to use it. Okay? All right. You can right away, if I give you this cable system, you can draw the equivalent beam, and you substitute right away. Like you can put this and this right away without saying the summation of the moment and all this stuff. So let's solve a direct application on the general cable theory. Okay, let's see this problem. So in this problem, it's like a cable bridge, like Golden Gate Bridge in California, something like this. Usually, actually, this is how the suspended bridges look like. You have a really huge tower here. Let's see example. And you have a tower here, and you have another tower here. By the way, sometimes this is a really huge tower. Like this tower, sometimes it reach up to 300 meters. It's like a real building. It depends on how big is your bridge. So you have a tower here and a tower here, and then you make a cable like this, and this cable goes up and go to an anchor here, and another anchor here. So in our problem, I told you I have these distances 60, 60, and 40, 40. And I have distributed load coming from the on weight of this cable is 0.6 kips per foot. And I ask you to calculate the maximum cable tension in BD and the tension on the cable AB. So this is AB, I have this is C, D, E. So I'm asking you to calculate the maximum tension in BD, maximum tension, not only the tension, the maximum. And also calculate the tension in AB. So first, this is, I can use, are you guys done with this part? Can I erase it? By the way, you can divide this cable here and start dealing with this one separately, assuming that there's a horizontal and vertical here. The thing is, there's a tension and this cable going that way. It's the same at the tension here. Both of them at the same. They balance each other. If they are not the same, so this support is balancing them. All right? It depends actually. It depends. Like if it's continuous or it's cut here and this one is supported separately and this one is supported separately. Okay? Alright, so I can apply the rule of general cable theory on this part. How can I do that? Okay, you are gonna take this part, it's like a cable here, supported here and supported here, and you have a load W equal to 0.6 kips per foot. I can draw the equivalent bending, the equivalent simple beam, and I can put the load on this simple beam, something like this, W equal to 0.6. So I know that did I give you the height? Yeah, I give you this, the side here. This is equal to H equal to 10 foot. All right, so if you want to know the horizontal force in this cable, like the horizontal force here or the horizontal force in any section, I know in the middle the moment is equal to WL squared over 8. That's what I know. So I can use the general cable theory and say that the horizontal force multiplied by the sag in the middle minus the moment in the middle is equal to 0. So I don't know the horizontal force, but I know H is equal to 10, and I know that the moment in the middle is equal to WL squared over 8 is equal to 0. So this is going to be equal to 0.6, and L actually is the whole L. It's like 60 and 60, 120. So 0.6 multiplied by 120 squared over 8 is equal to 0. So H is going to be equal to 108 kips. Does anybody have any question? By the way, you can solve it with the regular way. Like you can divide this and make this hinge and make this hinge and try to solve this by summation the moment left, summation the moment right, and all the stuff that you want to do. But I don't want to know the vertical reaction. I only want to know the horizontal reaction. So I got to that one first. Okay, so I found the horizontal reaction. The next step is, how can I find the maximum tension in this cable? So right now I'm not asking you the tension at C or B or D, I'm asking you about the maximum. Can you tell me where's the maximum tension in this cable?
Where the maximum angle is?
Where's the maximum angle?
At B or D?
At B or D. So this is the maximum angle. How about here? This is the minimum tension. The minimum tension is going to be equal to the horizontal force. Like if you have theta, yes, theta is equal to 0, so cosine 0 is equal to 1, so T is going to be equal to H. All right, can you tell me how can I get the angle at B? Like let's say I want to know the angle here. Theta. The thing is, to know that, I need to find what is the equation of this parabolic curve. So the equation of the parabolic curve, we can actually generate it. Like let's say we have an xy axis here. This is x and this is y. and this is like a typical parabolic curve has an equation y equal to ax squared. So if you know 2 points on this parabolic curve, you can find the value of a. That's what we want to find out, the value of a. So I know
D.
that
You know D. X equals 68, Y equals 10.
at d, yeah, well, I'm gonna make it general. I'm gonna say that this is all L, and this is L over 2, and this is L over 2. I know at x equal to L over 2, y is equal okay, like, alright, so the thing is, you can actually put the axes here, or you can put them here. I put them here in the notes, but here is gonna be different, but both are right, okay? So if you find it different, it's both are right. So here, if I put the x-axis here, at x equal L over 2, what is the value of y?
10.
Which is h, right? Because we are working with symbols now, okay?
Right, sure.
So this is h. So I can substitute here. Get this out of the way. And I can say that h is equal to a multiplied L over 2 all squared. So I can say that a is going to be equal to L squared over 4h, right? So I can say that y is equal to L squared over 4h multiplied by x squared. That is the equation of the parabolic curve. So if you want to find the angle theta here, so you have to find the tan theta, and tan theta is equal to dy dx at the point of interest. Right now I'm making it general. So can you guys tell me what is the derivative of this function?
I think A is wrong. A is wrong.
Yeah.
4H over L squared.
It should be backwards. 4H
Oh
over
yeah, yeah,
L squared.
okay, so I have it here, a,
They divide by L squared.
yeah, the 4 is up there.
1.
Alright, so
Just solve for A. When you solve for A, you divide by L
it's
squared.
gonna be
Oh.
4H over L squared.
4h over L squared. Thanks for.
Yeah,
Because
and then you have to correct the
A
top.
is
Okay, so
4H.
this is gonna be a multiplied by L squared over 4.
Alright.
So I'm gonna multiply 4h, it's gonna be divided by L squared. Thank you.
So you have to change A to like 8.
Oh yeah, this one.
4H over L squared.
4h over L squared. Thank you. So I have this, so I'm gonna get d dx of the function y, that is 4h over L squared multiplied by x squared. Can you guys get that? So it's gonna be 2 multiplied by 4h is gonna be 8h divided by L squared multiplied by x. That is the derivative. So this is equal to tan theta. So basically, if you want to find out the theta at any height, you basically come here, try to find what is the value of h and substitute, and divide this by L squared multiplied by 8, and know where's your x at. But right now, I'm interested at point B. So at point B, let's say theta at B is equal to tan inverse of where the value of h is equal to
0.
no,
Oh, 10.
the value of h is equal to 10, so I have 8 multiplied by 10, L squared, by the way, L squared is the whole L. It's like this to this, because this is L over 2, so I'm gonna have 120, and this is a squared, and this is multiplied by x. What is the value of x? So it's gonna be 60, and then you will find what is the value of this. So theta b is gonna be equal to 18.43. And that's degree. So I found theta, so the next step is to find the maximum tension. So that's gonna be very easy because I'm gonna substitute in the rule that we are memorizing, which is T is equal to h over cosine theta. So basically I can say that T at B is equal to h over cosine theta. I got h is equal to 108, and theta is equal to 18.43. So this is going to be equal to 152.76 kips. Does anybody have any questions till now? I believe the most difficult part in this problem is to find the angle theta. Doing some geometry, and then find the equation of the parabolic curve, take the derivative of this curve and substitute with the x at this point of interest, and then you will find the angle theta. Then you will find TB. All right, so the second part is to find the tension in this cable. This cable. And that cable is very easy. Why? Because I told you at first, oh, I didn't tell you, but at first I told you that this angle is 45 degrees. Or I can tell you that this height is 40 feet. Both are same. Okay? So if I give you this and I told you that, I didn't tell you, we already find it out that the horizontal is equal to 108. So the horizontal for the whole problem is gonna be 108. So basically, if you wanna find the tension in cable AB is gonna be equal to the horizontal over cosine theta of the cable. The horizontal for the whole problem is 108 over cosine 45 degrees, and this is gonna give us 152.76. By the way,
No. Is it?
oh sorry,
I don't
this
think-
one, sorry, when you calculate it, is 113.8. This is down at 152.76 kids. Okay? All right, so I believe that's it for now, and I believe we covered the whole cable section. So the whole cable section has two main rules. This one, T, and the other one is the general cable theory, that one. If you know both of them and you know how to derive a function of a curve, you will not struggle with this section. It's gonna be a piece of cake, all right? Okay, next time we are gonna cover arches. See you guys next time.
Thank you.
Just one second.